Right, so what are we going to do today? We're going to think about what is a mineral, what is a rock. We're going to think about the volcanoes, why they're important. We're going to look at the types of magma. We're going to look at types of volcano. Think about our tectonic settings again. This all comes back into talking about plate tectonics. And then we're going to talk about volcanic hazards. So, first of all, minerals. Minerals are extremely important. Our sort of human evolution has often been dictated by the minerals that we use. We talk about the Bronze Age, we talk about the Iron Age. Things like that have driven human history. Things like the demand for resources like that have governed wars and conflict, things like that. And today, if you cut off the American economy from its, well, not so much anymore, but when we were a big manufacturing economy, then if you cut off our supply of things like iron ore, aluminium is my way, you can call it what you want, then we're in trouble as an economy. Our economy runs on this. We're on the gold standard. So minerals are incredibly important, and not just the obvious ones that you think of every day that make up your laptop, that make up our seats and our buildings. So things like iron, copper, lead, zinc, but also non-metals as well, things like limestone, clay, we use in building and roads and everything else. So these things are incredibly important to society in general. So what is a mineral? It comes in lots of different types, but there are 5 fundamental things, and I think your notes only have 4, which is it must be naturally formed. We're forming lots of new minerals every year in the lab, but it doesn't really count as a proper mineral because it's not naturally formed. Must be inorganic, so it doesn't have that carbon-carbon bond that make up us, proteins, sugars, things like that. It must be solid, okay? And then it must have a specific chemical composition. So if we talk about limestone, what we're talking about is calcium carbonate. It has a specific chemical composition that we can name. And also it has this very characteristic sort of crystalline structure. And that crystalline structure gives it things like its symmetry, its shape, the strength of that mineral. And so these things are all very important when we think about minerals. So first iClicker question of the day is, based on that definition, based on those things, which of those is a mineral? Would it be ice, sugar, or mercury? Okay, so probably just a few more seconds for anyone else to vote. Okay, so let's see if we agree. We don't agree. Okay. So let's see what we can rule out. So let's go back to our list. So tell me, what is it about mercury that might mean it's not a mineral?
It's solid.
It's not a solid, it's liquid, so mercury can't be a mineral. What
temperature is that required for?
Oh, sneaky question from the front. Good thing, good thought. So he said, well, what about what temperature it's at? You're right that if we get colder, it would be a solid, then it would be a mineral. Good thought. Okay, so we're thinking about room temperature right now. What about sugar? Why might sugar not be a mineral? It is, we do get natural sugars, but what is it? It's organic. Okay, it's organic. It has these carbon-carbon bonds. So we can make sugar crystals, but it's not a mineral. So funnily enough, ice is our mineral in this example. And it exists at least briefly at room temperature, and definitely when it's colder than 0 degrees Celsius. So it's formed by geologic processes. You can see that it has a definite chemical composition. It's got H2O. It has a definite chemical or crystalline structure, and it's what gives it that beautiful 6-sided shape and the symmetry to it. It has a crystalline structure. It's a solid. It's naturally occurring. So it ticks all of our boxes. Okay, so ice in this definition is a mineral. Yes?
I thought we were talking about room temperature.
Ice, well, you can have ice existing briefly at room temperature, but yes. Okay. So not only is our crystals very important, but obviously they can be very beautiful as well. So this is not photoshopped. This is a real photo taken in a cave down from Mexico. And they were digging a really deep mine, and they broke into this chamber with these amazing crystals that have had just the right conditions to grow for a very, very long time. And they are just spectacular. It really looks like something out of Superman or a movie in some way. So these things can get big. Okay, so let's think about our common minerals, because minerals are really what make up rocks and what make up the earth. And so we have a lot of what we call silicates. If you look at the amount of silicon and oxygen in the crust, then they make up the bulk of the crust. And so silicates, which are that SiO4 4- little group, are what make up a lot of the Earth's crust, and what we're going to talk about today when we talk about volcanoes. So things that you might have heard of that are silicates are feldspar, quartz, clays, micas, things like that. Then we have oxides. Those are really helpful for finding minerals with metals in them, so things like iron oxides, aluminium oxides. We have carbonates. We have our limestones, things like calcium carbonate. We have sulfates, gypsum, and then we have sulfides, things like pyrite, which is that fool's gold, if you've ever seen fool's gold. So we have a whole bunch of different minerals. Don't worry too much about them, but they exist, okay? So what is a rock? We've talked about what a mineral is. What's the difference between a mineral and a rock? Well, a rock is naturally formed again, just like our minerals. It's non-living, so non-organic. It's solid, so we're still the same as our mineral right now. But the difference is that a rock is made up of a lot of different minerals. So it doesn't necessarily have one specific crystalline structure. It doesn't necessarily have one particular chemical formula that defines it. It's a mixture of lots of different minerals all lumped together. Okay? So, is concrete rock? So see if you can follow the definition again. Is all the concrete we see around here, is that rock? Couple more seconds. Okay. Oh, we've got a majority this time, and the majority would be right. Which criteria does it not meet from my definition? It's not naturally formed. We've made it. It is a collection of other minerals and stuff, but it's not naturally formed. We created it. Okay. So we have 3 different types of rock. And this is probably starting to sound familiar. We have igneous rocks. And igneous rocks are what we're going to talk about today. And they're formed by cooling and consolidation or crystallization of magma. And magma is sort of molten rock. We have sedimentary rock. And sedimentary rocks can be formed in quite a variety of ways. But fundamentally, they either form by chemical precipitation of dissolved material, so things like calcium carbonate can precipitate out of solution, halite, gypsum, things that precipitate out of seawater, or they can form by the deposition of mineral particles transported by water, wind, and ice. So if you go to the beach, you can see lots of sand that has been transported by water, and dunes are transported by wind, and ice travels and carries sort of particles along with it. So these are our sedimentary rocks. So once these things get sort of deposited by wind, water, and ice, or by chemical precipitation, they can form rocks. And then lastly, we have metamorphic rock. And metamorphic rock is what happens, well, it's what you get if you take an igneous rock or a sedimentary rock and you heat it up, or you put enormous amounts of pressure on it, and that's what you end up with. Okay? So what do you think? Which of those 3 do you think is the most important for the crust? What do you think it might be? I heard an igneous over here, and you would be right. Igneous rocks make up 95% of the Earth's crust. So igneous rocks make up 95% of the Earth's crust. We don't necessarily see all of that because a lot of those igneous rocks are actually much deeper down. What we tend to see at the surface is the effect of our wind, of our ice, of our water. It's the sediment and the sedimentary rocks. That doesn't mean that deep down we don't have enormous amounts of igneous rock. So let's talk about it some more. And first of all, we need to talk about magma. So magma is this sort of definition of mixture of molten rock, suspended mineral grains, so it can have bits of solid in there as well, and dissolved gases that forms in the crust or the mantle. And we're going to look at the different environments that magma can form in today. Guys at the back, do you want to be quiet, please? Oi, you three. Shush. Okay. So lava, what we think of as lava, is basically just magma that reaches the surface. So it's magma when it's within the crust or the mantle. Anything that makes it out to the surface is called lava. And we characterize magma based on its composition, based on its viscosity, which is the ability to flow, and the temperature. So we're going to look at 3 different types of magma. We're going to simplify it a little bit. We're going to look at basaltic magma, andesitic magma, and rhyolitic magma. So these are the more complicated words that your note card is for the exam. So the main fundamental difference between each of these is that as you go from basaltic magma, that has a composition that's 50% silica. So that combination of silicon and oxygen is a silica, and basaltic magma is 50% that. If we go to andesitic magma, it's 60%. If we go to rhyolitic, it's 70%. And that actually has a very important control on things like viscosity. So who's been to Hawaii and seen the lava flows? Yeah? How did they flow? Did they like clump together, or did they go relatively smoothly and fast? Yeah? So if you see when they're sort of first coming out, they flow pretty nicely. They're slow, they're rock, it's molten rock, it's never going to flow like water, but it flows relatively smoothly, it flows relatively fast, and that's what we call sort of low viscosity. So when it flows, when it's sort of runny, that's low viscosity. The andesitic in the middle is medium, but then when we go to rhyolitic lavas don't flow. They're really blocky, and they're really sort of sticky, and so they just clump together at the top. And then eventually a whole bunch of them will sort of slide off the side. But it doesn't flow. It's just sort of clumps there in the middle. And the reason that we have different amounts of silica and so different viscosities is because we have a different amount of melted continental crust going into each of those 3 different magma types. So with basaltic magma, we really don't have any a tiny bit of continental crust that's melting and forming this magma. In andesitic, we have a little bit, and then in rhyolitic magma, we have much more continental crust melting and forming the magma. And why does the amount of continental crust matter? Because remember, our continental crust is sort of lighter, it has more silica in it than our ocean crust, which is denser and easier to sink back down. So that's why continental crust is important. And so I want you to have that in your mind when we think about the different places where we have volcanoes and the processes that are happening at those boundaries and forming our magma. And then the last thing that changes with each of these magma types is the volatile content. And when I say volatiles, I mean gases. So things like carbon dioxide and water vapor, which are the main gases in our sort of magmas. And obviously you can imagine that if something is quite runny, how easy do you think it is going to be for gas to escape from that? Pretty easy. If it's really sticky and it won't flow, it's going to be much harder for those gas bubbles to escape out. Yeah? Maybe? Good. Okay. So, thinking about this, if basaltic magmas are runny and they don't have much gas content, and we can compare that with the rhyolitic magmas that have high gas content, and they're really sticky and blocky, which do you think is likely to be more explosive? Rhyolitic. Because we're basically building up a pressure cooker, right? We have a lot more volatiles, we have a lot higher gas content there. We're not letting it escape, and so it can build up and can build up, can build up, and goes bang in a big way. Whereas Hawaii doesn't do that. Hawaii has more basaltic magma, and so gases can escape pretty easily, and it also just flows out pretty nicely. So there's no sort of pressure to build up and explode. So in terms of our eruption intensity, basaltic magmas don't really create much sort of danger to us. We can get out of the way pretty easily. Their eruption intensity is pretty low. Then we go into medium for andesitic. Andesitic is always the medium one, unfortunately. And then rhyolitic, we have big, big explosions. To be honest, andesitic explosions you don't want to be in the way of either. They go bang in a very big way too. Okay, so let's think about where igneous rocks are. So I've already said that at the surface we don't necessarily see them, but they actually make up 95% of the Earth's crust. And so where is that? It's all deep down. And so we have two different types of igneous sort of settings. We have intrusive igneous rocks and extrusive igneous rocks. And which of those two terms do you think, or can you read quickly enough? Which of those two terms do you think describes rock that escapes from the top? Extrusive, yes, okay. So extrusive rocks are rocks that spread out at the surface. They're erupted at the surface and they cool down at the surface. Intrusive rocks cool down inside the crust. So hopefully those are two easy ones to remember compared to the others today. I don't want you to panic and memorize all of these different terms like laccolith, pluton, batholith. Those aren't necessarily important. All I want you to realize is that the magma and the lava that escapes out of the top of your volcano is a tiny, tiny, tiny fraction of the molten magma that's actually down there, okay? So your little volcano that you're seeing is sort of dwarfed in size by the amount of magma that you can get down, so deep down, okay? So extrusive igneous rocks are what gets erupted at the surface. So things like lava flows, ash, what we call tephra, which are sort of bits of rock that you see exploded out of the top. And they cool down really quickly. So they have very, very small crystals. Did anyone have to grow crystals at school when you were little, like the copper sulfate crystals? Yeah. Did you wait for one day or did you wait for much longer? Come on, dredge your memory. How long did you want to wait if you wanted big crystals? A long time. They take time to form, okay? And so the rocks that get erupted at the surface have very, very tiny crystals. That means that the intrusive rocks, the ones that cool down inside, they cool down much more slowly because there's all of this rock around them insulating them. It keeps them warmer for longer, so they slow down much more, or they cool down much more slowly, and so they have time to form really nice, beautiful crystals. Okay?